Hello, this is Dr. John, your physics and math professor, and today we're exploring another circular motion equation. This one we're looking at an old carnival trick that may have been done 50, 100 years ago, where people would come down this giant ramp. Lots of people would be watching this giant ramp and then whip around this curve to see if they could stay on the ramp. This ramp here, a bike goes around a loop with a diameter of 10 meters. We want to know how fast the bike needs to go. Obviously, you want to go quite fast, but this ramp, you want to stay on it as well, so you're going to have to be able to control your bike. How fast do you need to go? Well, this is a little bit different than your Ferris wheel problem where everything is locked together. So here we have the circle, everything's locked together, and everything has the same velocity. So a Ferris wheel, for example, would have the same velocity everywhere all the way around because it's all hooked together. However, here, the bike would have to have a higher velocity at the bottom when it goes up the loop than at the top. So what we're concerned about in this case is specifically the velocity of the bike at the top. Some of the kinetic energy from the bottom here would be converted to potential energy at the top. However, the bike would still need to have enough velocity so that the outward force, that fake gravity, the centrifugal force, the pressure that the bike would feel upward would have to be equal to the force of gravity that the bike would feel downward. That would be like the minimum amount of velocity the bike would need to have. At that point, the wheels would just barely touch the surface. There would be no actual friction. And for just a second, it would just sort of leave the surface. So you'd want to be a little bit faster than that. So what we're doing is we're trying to find what velocity the bike would need to have at the top. A longer, more complicated calculation would show us what velocity the bike would need to have when it's entering, but we're just doing the little bit simpler calculation of the velocity at the top. So as I mentioned before, the upward pressure or acceleration that the bike would need to have, what we're talking about here is a force. So the force is going to be equal to mass times acceleration, and here the force is going to be equal to the mass times acceleration. And what we want is this downward force of gravity that the bike's going to feel right up here, this here, to be equal to the upward force, the centrifugal force that the bike is going to need to produce by its velocity as well. So remember that this is going to be equal to this. So the two masses are going to equal. They're going to cancel out. So all we're left with is this. The acceleration upward, which is the same as the inward acceleration, the centripetal. Notice we're pedaling with a bicycle, so that's convenient. The centripetal acceleration the bike would have to experience in this direction to keep going around. Those two, the outward force, the force of gravity that the bike would feel in pressure upward because of its going around, and the inward acceleration the bike would need to have to go around here. Those are equal to each other in magnitude. They're opposite in direction. But what we're looking for is the magnitude of this centrifugal force. That has to be equal to this. And since the masses cancel, we want the v squared over r, this upward acceleration, or the inward acceleration, they're equal, to be also equal to the acceleration of gravity. So we want v squared over r to be equal to g, or 9.8. So let's write that out. M v squared over r to be equal to mg. I mentioned that we want to get to this place, so we'll just cancel the m's on both sides. And then we'll multiply both sides by r. So we're going to have v squared is equal to rg, or v is equal to the square root of rg. And what are those values? Let me just erase this. I'll write that in here. D is equal to the square root of 9.8 times r. Now we've mentioned that the diameter here is 10, so the radius, this radius would be half of that. The radius would be 5. So we're going to multiply this by 5. 9.8 times 5 is 49. We want the square root of 49. Square root of 49 is 7. 7 times 7 is 49. So the velocity you're going to need here at the top, the velocity is going to be equal to 7. And then let's look at the significant figures. Well, we're given here that the loop has 10.0 meters. So even though this sort of looked like an exact answer for us, we still want to put it into the significant figures here as 7.00 meters per second. That would be the velocity the bike would need at the top to stay on the loop. I hope that helped. If it did, like and subscribe, and I will see you in the next video. Bye-bye.